You got a couple applications here. The first one is of what does that look like to you? It's a speaker, right? Okay, that's a speaker that maybe is in your car, or maybe that's plugged into your iPhone, or maybe that's plugged into an old CD player or record player, or something like that. Speakers put out sound so that we can hear it, but the signal to the speaker is not sound. Sound does not leave your iPhone, go into your speaker. It's electricity that leaves your iPhone and goes into the speaker. That's why it's usually connected by a wire. So electricity goes through the wire and then goes into the speaker and then gets converted to the sound that was trying to be produced by your phone. In this case, they have it drawn such that the electrical signal is going this way through this wire. And then it's going to curl up here around this coil. Now, this coil, it's difficult to see the details of this coil. So it'd be pretty hard for us to say that this is the north end, this is the south end. Okay, that doesn't really matter to us right now. It becomes an electromagnet, right? When you wrap wire around something and you got current going through that wire, it becomes an electromagnet. Current goes out the other end, back to the iPhone, done. But notice inside and surrounding the electromagnet is a permanent magnet, this yellow permanent magnet. Now, if the polarity of this electromagnet is one way, then it's going to cause the permanent magnet to be repelled this way. Right? If you got a certain polarity, then the permanent magnet repels to the left. If the polarity of the electromagnet is opposite, then this permanent magnet, the yellow one, gets attracted to the right. So in other words, we can cause this permanent magnet to go one way or the other way, depending upon the magnetic field in this coil, which is dependent upon the electric current that goes through the wire, which comes from your iPhone or your CD player or whatever it is, your 8-track player or whatever it is. Now, connected to that permanent magnet is this thing that we call a cone. This cone is usually made out of like a felt or a cardboard. And as this permanent magnet goes back and forth, depending upon the strength and the direction of the electric current, remember that as the music is playing, the electric current may reverse direction or change strength so that it changes the direction and strength of the magnetic field, so that it changes the amount of movement and the direction of movement of the permanent magnet. This cone goes back and forth with the permanent magnet since it's attached. When the cone goes this way, gets pulled back, then it creates a low pressure of air in front of it. When it gets pushed forward, it creates a high pressure of air in front of it. That's what sound is, right? It's areas of high pressure and low pressure. When you hear my voice right now, you're hearing not the air coming from my throat into your ears, because that would be gross, but rather you're hearing the variations in air pressure that are caused by my larynx. Okay, I'm causing variations in air pressure, which the variations in pressure are transferring to your ears, not the air itself. Because that's what happens here. Instead of my voice box vibrating back and forth, causing variations in pressure, it's this cone vibrating back and forth, causing variations in pressure, which is sound. Okay, we hear the sound that the iPhone was meant to produce. It sends out an electrical signal, and then that electrical signal gets converted to a mechanical and then a sound signal. Got another one for you here. This is a doorbell. It could be a fire alarm. There's a switch up here. When we close the switch, closing the switch means the switch is turned on. Like right now, this switch on the wall is closed. Right now it's open. When it's closed, we complete the circuit. Okay, so we've got, right now, this switch is open, but when we close it, maybe we hold on to it, maybe it somehow stays closed by itself, like a fire alarm would, right? Stays closed by itself. Then the bell goes ding, 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 as long as the switch is closed. So how does it work, though? Well, you've got electric current leaving the negative terminal of the battery. This is the positive terminal. The long end is the positive, right? Electric current leaving the negative, coming around here to this make-break contact right there that is attached, or not attached to, but touching this piece of steel that is connected to this, let's Do this again. Touching this piece of steel that's connected to this thicker piece of steel, which is connected to this hammer. So we got electricity that's leaving the negative side of the battery. It's coming around here. It's making the contact here. It's going through this green piece of steel here, and then it's cutting over here around the coil, back here, back through the closed switch, back to the power supply, and so on. So we got a complete circuit here. Now, as electrons are going around these coils of wire, they become electromagnets, right? They become magnetized with a certain polarity. If we could see the detail on this better, then we could predict which end would be north, which end would be south. What happens now? Well, as these coils become electromagnets, this green piece of steel gets attracted to it because it's ferromagnetic. As it gets pulled to the right as a result of that attraction, the hammer hits the bell. What do we hear? Ding. That's it. So how do you hear the ding, 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 ding? Okay, let's say there's a fire in the school. We hear ding. It's probably not going to be enough to evacuate 800 people. Okay, we need it to continue going. What happens now, though? Look, this make-break contact has been broken. The circuit is no longer. These electromagnets aren't electromagnets anymore because there's no current going through them. They're just coils. So now this spring that we have right here, pulls this green piece of steel back away from these coils that are no longer electromagnets. It makes contact again. The electric current starts flowing again, remagnetizing the coils, attracting this piece of steel. Ding, breaks the circuit. Spring pulls it back, completes the circuit, remagnetizes, attracts. Ding, breaks the circuit, demagnetizes. Spring pulls it back, completes the circuit, and so on and so on and so on. What ends up happening here? It automatically itself breaks the circuit and completes the circuit. Breaks the circuit, completes the circuit. Makes them magnets, makes them not magnets. Makes them magnets, makes them not magnets. Causes this thing to go back and forth like this. Ding, 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 ding. Maybe 60 times per second. That's the bell that you hear. As long as the switch is turned on or closed, then this is going to keep going back and forth as a result of repeated making and breaking of the circuit.